Photoelectron spectroscopy, very commonly just referred to as PES on the AP exam, is a very, very commonly tested topic. It's not covered in general chemistry. And what it does, the reason that we're doing it right after electron configuration is because PES is a way to look at a graph and to determine information about the electron configuration of the atom or ion in question. So photoelectron spectroscopy is used to gather data about the specific electronic structure. So again, the electronic structure is the electron configuration of an atom by analyzing the electrons that are ejected by what's called the photoelectric effect. So PES produces a graph that gives important information about the structure of the atom. So it's a way to interpret data and extract information on the atomic structure of that data. Okay, and as we talked about the other day, we know that light is made up of little packets. And remember, the little packets are called quantum or quanta of energy called photons. And each of those photons has an energy that we can find by taking Planck's constant and multiplying by the frequency. Okay, the photoelectric effect is actually something that Einstein came up with, is that when you shoot a beam of light at something, the light ejects electrons from a material. And this requires the photon to have enough energy to eject the electron. And what PES does is it determines the energy needed to eject the electrons from the material. So in photoelectron spectroscopy, light is directed onto a sample, which causes the electrons to be emitted, and then the energy of those electrons is measured. This is kind of just two more details. This isn't necessarily important. The difference between the energy of the photons and the kinetic energy corresponds to the energy needed to remove the electrons. And the intensity of the photoelectron signal at a given energy is a measure of the number of electrons in that energy level. So the intensity is sometimes related to the number of electrons, and that's going to come back here in just a little bit. So when you look at a PES diagram, there's three main things that you need to understand. The first thing that we need to understand is that in a PES diagram, there are peaks. And so a graph similar to this one down here at the bottom, this is actually a fairly uncommon one, which we'll talk about here in just a second. But in a PES diagram, typically you have a diagram that looks like this. And then on the left-hand side, typically it will say the number of electrons. It may also say the intensity. Remember up here we had said that the intensity of the photoelectron signal at a given energy is a measure of the number of electrons. So it may say either one of those, but they generally mean the same thing. And then down here, typically the energy they're referring to is called the binding energy. Okay, and what you're going to have is you're going to have little peaks. And so you'll have a peak that comes up right here, and then maybe a little space, and then another peak that comes up right here, and then maybe another one that comes up right here. And obviously they look much prettier than the way I'm drawing them. But those peaks, and typically they have points at the end. They're not rounded at the end. They have some type of, they come up and have a little peak there, like so. Anyway, what those peaks represent is each peak represents a subshell. For example, the first peak, and when I say the first one, I mean the farthest one to the left, is always going to be the 1s peak. Okay, so when you look at a PES diagram, that first peak is the 1s peak. So I took that one out on accident. So for example, here we can see that this first peak here refers to the 1s peak, and then this peak here refers to the 2s peak. This peak here refers to the 2p peak, and if there was another one, there would be a 3s peak, etc. So as you're looking at these peaks, you know that it's starting from the 1s subshell. So each peak represents a different subshell. Now, if, for example, they were going to try to mess with you a little bit, they might start and they might say, the PES diagram of, let's say, sulfur is shown below. But they might start at the 3s because there'd be so many peaks. They might just start with 3s and just show you the 3s and the 3p peak. So it doesn't absolutely have to start with 1s, but just in terms of saving space, if they do ask a question about an element that's farther down on the periodic table. It's kind of like a valence shell electron configuration. They might not start until later on. Okay, so each peak represents a subshell. Typically, it will be the 1s that starts and then the 2s. You'll notice here, even on this one down here, you'll notice that the way that they graph these, they start when these numbers here on the bottom start with big numbers over here, and they go down to smaller numbers over here. And the reason that they do that, that's kind of opposite of what a typical graph looks like. The reason that they do that, though, is because so they can start with the peak that's closest to the nucleus. If you think about it, what electrons are most attracted to the nucleus? Well, the 1s electrons. They're the closest, according to Coulomb's law. The smaller the distance, the greater the force of attraction. Okay, and so the binding energy is the greatest in the 1s electrons, and then the 2s, and then the 2p, etc. So they start with big numbers on the left-hand side, and they get to smaller numbers as that binding energy, that the attraction that the electrons feel to the nucleus goes down. Okay, so point number 2 here. Typically, not always, but typically the height of each peak represents the number of electrons in that subshell. Okay, again, every single question I've seen about PES on the AP test has been that way except one, which we'll see here on the next page. The higher the peak, the more electrons are in that particular subshell. For example, a 4p subshell that is completely full would be much taller, should be exactly 3 times taller actually, than a 4s subshell that is also completely full. Now, how do you know how many electrons are in there? Well, you look at that first peak because you know, let's say it's, for example, nitrogen. Well, you don't know if it's nitrogen, but you know that the first peak, unless they tell you something different, let's say there's lines like this, and the first peak goes, it comes like this, and then it just goes up to here. And then the next one goes up to here, and then the next one goes up to, let's say, here. Okay, you know that this is the 1s peak, and that peak has that subshell, that 1s subshell, has 2 electrons in it. So therefore, that peak, each dash therefore represents 2 electrons. So here's our 2s peak that also represents 2 electrons, and this peak here goes up to the 3rd line. And so if each line represents 2 electrons, then this subshell, which is the 2p subshell, therefore has 6 electrons in it. So this element is clearly not nitrogen. It's the element that has the electron configuration of 1s2, 2s2, 2p6. Okay, which obviously is neon. Okay, number 3. The further the peak is to the left, the greater the binding energy. We talked about that. That's why those numbers are bigger. The farther it is to the left, the greater the binding energy. For example, the carbon peak X, which is right here, is farther to the left than the boron peak X, which is here, because carbon has a greater nuclear charge. Okay, carbon's got 6 protons, boron's only got 5. So those 1s electrons, remember this is the first peak for each of those elements. So the 1s electrons in carbon are more attracted to the nucleus than boron is. Again, think of Coulomb's law. The greater the charge, the greater the force of attraction. So according to Coulomb's law, carbon's 1s electrons are more attracted to the nucleus than borons are due to the greater nuclear charge. Remember, nuclear charge just means protons. Don't think of that anymore than you need to. Nuclear charge just means the number of protons. Okay, so let's take a look here at some questions. So the first point here says, suggest a reason why the boron and carbon peaks have been paired together in 3 groups labeled X, Y, and Z. Because these are the 1s electrons, these are the 2s electrons, and these would be the 2p electrons. So the X are the 1s, the Y are the 2s, and the Z is the 2p. Okay, the second point, explain why the carbon X peak is at a higher energy than the boron X peak. We already said that because the electrons are more drawn to the nucleus. The binding energy is greater in carbon because carbon has a greater nuclear charge. It has more protons. Okay, the third point. Why is the boron Z peak, so this one right here, why is it half the height of the carbon Z peak? Because in the 2p subshell of boron, it's only 2p1. For carbon in the 2p subshell, it's 2p2. And remember, the higher the peak, the more electrons there are. So since there's only one electron in the 2p subshell, boron is only half as tall as carbon. And of course, if we had nitrogen in there, the nitrogen peak would be even higher than the carbon one would be. Okay, and then if one were to superimpose a third PES plot on the same axis for elemental nitrogen, okay, what would that look like? Okay, so here's the questions. Relative to carbon's X peak, where would nitrogen's X peak appear on the axis? So for the 1s electrons, where would nitrogen be? In terms of those electrons right there, would nitrogen be farther to the left, right in between these two right here, or would nitrogen be to the right? Again, think about Coulomb's law. Nitrogen has more protons than either carbon or boron. So therefore, nitrogen's peak would be even to the left. It would have more binding energy than carbon's does. Okay, the second question. Relative to carbon's Z peak, so now we're over to the 2p subshell here, what would the height of nitrogen's Z peak be? It would be basically 50% taller than carbon's because nitrogen is 2p3. So it would be farther to the left because it has more protons still. All of carbon's are to the left of boron. So all of nitrogen's would also be to the left of carbon's. So it would overlap here, but basically it would be kind of right in here, and it would be even, taller than carbon's peak. Okay, and then last question. Identify the electrons that are associated with each peak in the boron plot. Again, we already talked about that. The X, 1s, 2s, 2p. Okay, now here's a different one. Again, this is the only time I've seen a question like this that that the peak doesn't relate with the number of electrons. This peak X, is clearly much, much taller than peak Y. More importantly, though, and what this problem did is it messed people up because they went, well, wait a minute, why is that peak so high? What's more important is that peak X is way farther to the left than peak Y. That's really the important key here, is that X is way, way farther to the left. So it says a sample containing atoms of carbon and fluorine was analyzed using X-ray photoelectron spectroscopy. The portion of the spectrum showing the 1s peaks, nothing else, only the 1s electrons for the two elements is shown above. Which of the following correctly identifies the 1s peak for fluorine atoms and provides an appropriate explanation? So first of all, we have to think, which 1s peak, again, both of these are 1s, is going to be farther to the left? Is it going to be carbon or is it going to be fluorine? Okay, and because they're in that same period, and we know that fluorine has more protons than carbon does, that the 1s electrons of fluorine are much, much more attracted to the nucleus than carbons are. So therefore, we would assume, therefore, that peak X must therefore be fluorine simply because fluorine has more protons or has a greater nuclear charge than carbon does. So therefore, B is the correct answer. Okay, here's another example of this. Which of the following best explains the relative positioning and intensity of the 2s peaks in the following spectra? So you've got one, so these are the 2s peaks. So the 1s, they aren't even showing them there. So the 1s aren't even there. These are only the 2s peaks. So we've got this one where it's farther to the right, and it's lithium, it shows. And the other one, beryllium, is farther to the left. And we notice it's also taller. So first of all, why is beryllium's taller? Well, again, unless it's this one question right here, we know that if the peaks are taller, then it has to be because it has more electrons in it. And when we look at lithium, lithium is 2s1, beryllium is 2s2. So that explains the height. This one's taller than this one because beryllium has more electrons than lithium does. Okay, but now why is beryllium so much farther to the left than lithium is? Again, comes back to charges on the nucleus. Okay, beryllium's peak is farther to the left because the 2s electrons in beryllium are more attracted to the nucleus than in lithium, because in beryllium there are 4 protons, in lithium there are only 3 protons. So, which of the following best explains the relative positioning, so that means the fact that beryllium's to the left, and the intensity, which means, again, that's the number of electrons. So, we can look at that. So, answer A, beryllium has a greater nuclear charge. That's true. That's why it's farther to the left. And more protons in the 2s orbital, also true. So, therefore, that's why it is taller. So, A is the correct response. Okay, so let's go ahead and get rid of this. Let's look at last year's AP test. So on last year's AP test, and this is something that you guys can go to as well. When we go to this, we can look and see AP Chem. We want to go to their new tests. Scroll down here. Maybe we go to last year. So 2000, this is the 2018 test. We're going to go to the free response questions. Usually every year, whether it's a free response or multiple choice question, PES is something that they do test every single year. So let's go. It was the very last question, if I remember correctly. Can get there. There we go. End of the exam. Okay. So 2018 AP Chemistry Free Response questions. So this clearly is a PES diagram here. So number 7, the complete photoelectron spectrum of an element is represented above. A, identify the element. B and C we haven't learned about, so don't worry about that yet. But if we look here at identifying the element, remember there's 2 things that we're looking for. First of all, notice the bottom. It says binding energy, and then on the side it says relative number of electrons. Again, it could say intensity, but in general it will say number of electrons. So you'll notice, what's this peak right here? We're at the 40. That definitely is the 1s electrons. Okay, the next peak over is the 2s electrons. And then the third peak over, don't confuse that. Some students did. Some students thought this last line right here was like this line right here, where it's not. That is another peak in the PES diagram. If this last line here were just a line, then it would just be 1s2, 2s2. This would be beryllium. Okay, and some of my students, unfortunately, did write beryllium down as that answer, which it is not. Okay, coming back here though, 1s2, 2s2, and clearly each line represents 1 electron. So this one goes up 1, 2, 3. So it's got to be 1s2, 2s2, 2p3. And so now we go to the periodic table and we look and we go, what element has an electron configuration of 1s2, 2s2, 2p3? Clearly nitrogen. Okay, and that question, that's a pretty typical PES diagram type question on the AP test. They're usually, if you understand binding energy, if you understand relative number of electrons, usually these are pretty easy questions to answer. And again, that's the most recent question that we have available to us. So hopefully you can see that, okay, yeah, I understand. I can understand binding energy. Again, just make sure, and I feel like they could have done a better job on making that peak more visible as a peak, but clearly they did not. So notice the difference, though, between the 1s and the 2s electrons. The 1s is held so strongly to the nucleus compared to even the 2s and the 2p electrons. And the farther away you get, the less and less attracted those electrons are. So the 1s electrons are always the most attracted ones to the nucleus. Okay, and if you were to put, for example, oxygen on there, oxygen has more protons, so oxygen's 1s peak would be a little bit to the left of nitrogen's. The 2s peak also would be the same height, but a little bit to the left of their nitrogen's 2s peak. And then the 2p peak would also be a little bit to the left of this peak, and it would obviously be taller. It would have one more line, and it would be taller, and it would be farther to the left. And that's basically what you need to know about PES diagram.